Hello and welcome to today's colloquium. It's our privilege to have our very own Professor John Colton. Professor Colton was an undergraduate student here many years ago. And when he finished, he earned a PhD at UC Berkeley doing condensed matter stuff. And after that, he did a postdoc at the Naval Research Labs in Washington, D.C. And then he was a faculty member at the University of Wisconsin in La Crosse. And we're so lucky that we recruited him to come back here. And he's been here since 2007, and we've never been happier. Welcome, John. We're glad for your talk today about hybrid organic, inorganic semiconductor stuff.
All right, thank you. Is it going to be best if I dim the lights then? Yeah. Okay. And hopefully the people online can hear everything okay as well. I guess type something into the chat if you can't hear me. I don't know how it's going to work. Anyway, okay, so I'll be talking about this work that we've been doing over the last couple of years. A lot of this is, or almost all of this is going to be a direct result of this collaboration with the University of Utah with Cameron Hansen, who was an undergraduate here. Yes? Sure. Cameron was an undergraduate here, got his PhD from the University of Utah, and is now a postdoc there working with Dr. Luz Whitaker Brooks. And he just walked in the door right back there. And there's a lot of BYU students who have contributed to this research, some other collaborators and people that I worked with on my sabbatical to the National Renewable Energy Laboratory, which I'll talk about in a bit. So just to introduce myself a little bit, for those of you who don't know me, I have a wife, 2 daughters and a son-in-law. I like to do a lot of outdoor things, including play ultimate frisbee. This is a picture from this week. This was summer term. I'm the advisor for the a cappella club and really enjoy singing as well as advising. And I also play table tennis, having finished second in the BYU tournament that was a week ago. Thank you. Yeah, I won it a year and a half ago, so I'm not sure. Should I be happy or sad that I finished second? But anyway, it was a fun experience. I do research in semiconductor materials. You can see what my lab looked like maybe earlier this year. It's a little bit different now. Actually, maybe it was longer ago than that. We do a lot of optical experiments, and there's a bunch of lasers scattered around the lab, most of which you can't see, but here's one right here. Here's one right there, if you know where to look. And detectors, and we do things at low temperature using cryostats, and sometimes high magnetic field using some big magnets. So as I was thinking about how to present this talk, I remembered 3 pieces of advice on how best to give a talk. So the first piece of advice was, I forget actually who said this. It was at some conference talk that I was at, and he said, when I give talks, I think when you give talks, you should do them like this. At first, you should say things that everybody knows. By the middle, you should be saying things that only you know. And by the end, you should say things, get into stuff that not even you know. The second bit of philosophy was, I think this is from my junior high school, one of my junior high school teachers, and he said something like, first you should tell them what you're going to tell them, then you tell them, and then you tell them what you told them at the end. You may have heard that one before. And I think the last bit of advice comes from, maybe it was my wife's grandpa, who said, stand up, speak, no, you gotta get this right. Yeah, stand up, speak up, then shut up. So I think 2 and 3 are more relevant than the first bit of advice. Anyway, for my talk, I'm going to get into a bit of semiconductor physics, including how solar cells work. I'll talk about these specific materials that are these hybrid organic inorganic semiconductors, including some important results that we've obtained over the last couple of years. I'll talk a bit about the sabbatical I was on at NREL, National Renewable Energy Lab, and then some of the future things that we've got going on, for example, chiral materials. So semiconductors are very important technological materials. They conduct a little bit, so they are not fully conductive, but they're not fully insulative either. And you can make transistors or diodes or things out of them that form the basis of computer technology. Silicon is probably the most well-known semiconductor, but there's a lot of other semiconductor materials that are involved with what's called optoelectronics, which is the integration of optics with electronics. So if you talk about fiber optic communication, you need to have things that send out the information with light, and things that receive the information with light, and then coordinate that between the light and then the computer circuitry, the electronics that does stuff with it. And that's the type of semiconductors that I study. And I'm studying materials properties, so I don't actually like build LEDs or lasers or things like that, but I study the materials that people can use to make things out of. To explain semiconductors, first I want to start with atoms, because I figure everybody's at least a little bit familiar with atoms. In the hydrogen atom, you get these series of energy levels, for example, that I think I learned in high school chemistry. And you can get electrons hopping between energy levels. In order to hop up in energy, they have to absorb energy from something like a photon. And if they hop down in energy, then they emit a photon. So you get a series of discrete photon line or spectral lines in both the absorption and the emission spectrum of the atom. If you have a hydrogen molecule, it's a similar sort of thing. You get energy levels that shift around a bit. And in a molecule of hydrogen, you have two electrons, so you have two states that are occupied instead of just a single state that's occupied. Well, a solid, in some sense, is just a really, really big molecule. And you have a bunch of energy levels, but because there's so many atoms interacting to form a solid, the energy levels are so closely spaced as to appear like a continuous band of energies. And you have a bunch of electrons, and they fill up some states that are lower energy, and there are typically some empty states at a higher energy. And there's in a semiconductor, there's a gap between the filled and the empty states called the band gap. In a hydrogen atom, you get different wave functions. Again, going back to high school chemistry, I think we had a poster like this on the wall, something like that. These are depicting basically the probability of where you might find the electron in the hydrogen atom for different energy levels. This is a complicated thing because it involves 3 dimensions, and I decided to make a model of an atom in 1 dimension. So it's kind of a similar sort of thing. This is my atom. This is a particle in a finite square weld model, for those of you that have had 222. And I used actually computer code from Physics 430 in the lab manual. There's a section of how to calculate energy levels and wave functions from the Schrödinger equation. And you get some energy levels. Here are some energies and wave functions that look like this in 1 dimension. So a simpler version of what was on the previous slide. And now I've got my hydrogen molecule, which I'm modeling as 2 atoms close to each other. And here are the first 2 energy states that you get, and the wave functions of them. And what I want to point out here is that the energy of these 2 states are basically related to the energy of the ground state of a single atom. It splits a little bit in energy, and you get two closely spaced energy levels right around this instead of two widely spaced energy levels. You get higher energy levels as well, but I'm just focusing on the lowest states at first. Okay, well, a solid, like I said, is just a really big molecule. So here is a solid that is 24 atoms long. So I'm modeling this as 24 square wells in a row. And what happens when you calculate the energy levels is you get, again, the energy level of a single state kind of splits into a bunch of very finely spaced energy levels. And I've just labeled these by the state number. And you can see they go up in energy in this interesting sort of shape. But the point is that you get a bunch of finely spaced energy levels. In an actual solid, you have way more than 24 atoms. And so the spacing between the energy levels becomes so fine that, again, it looks like almost a continuous band. Here are the wave functions for the four lowest states that I've plotted there. And I'm plotting here both the wave function itself, which is in blue, and then also the wave function squared, because that relates to the probability that's in red. And I want to point out, first of all, that it kind of goes up and down with the location of these atoms. So there's kind of 24 fast oscillations here. So it's saying the electron's most likely to be found close to one of the atoms. But then there's also other interesting things that happen. And if you look at this longer range modulation, you get basically sinusoidal behavior in that long range modulation. And if you define the wave number as 2 pi over the wavelength of this long range modulation, then you can calculate wave numbers for these different states. And it turns out these energy levels here are exactly in order of increasing wave number. And so when we talk about energy levels in semiconductors, we usually talk about both energy and wave number. And this wave number is closely related to conservation of momentum. Basically, you just multiply by Planck's constant. And then you have to, in real materials, think about X, Y, and Z directions. But doing all of that and using even more sophisticated models of atoms than little boxes, people can calculate what's called the band structure for semiconductors. So here's an example. This is gallium arsenide, which is probably the second most famous semiconductor after silicon. You can see it has tetrahedral bonding. And then you have alternating atoms between gallium and arsenide atoms. And down here at the bottom, if you focus again on the lowest states, this looks a lot like this. Starts off and rounds off. And these are complicated letters here and symbols just to indicate different directions. So X here means you're going, the momentum is in the X direction, basically. Okay, well, because you have so many atoms, you have so many closely spaced states, but you also have lots of electrons that are occupying these states. And in this particular material, you have these bands at the bottom that are filled, and these bands up at the top that are empty. And the boundary between the filled and the empty states is where the band gap occurs. And these states down here are filled, these states up here are empty. And the band gap is what governs the most important properties of semiconductor absorption and emission. If you send in a photon with at least this much energy, it'll bump an electron from one of these filled states into one of these empty states. And if you have an electron up here in one of these states and there's an open space down below, it can go back down and emit light. And you can also you can absorb higher energy photons. Again, you need to take an electron from a filled state to an empty state, and that gives you absorption. So this is the connection between the optics, the optical properties, and the electronic properties inside the materials. When you have different types of semiconductors, they'll have different band gaps, and you can even alloy materials together to get whatever band gap you might want. So when I first got into semiconductors and saw a plot like this, I just thought this was the coolest thing. You typically need to find materials that are compatible with each other as far as the lattice parameter, which is basically a measure of how closely spaced the atoms are. But for example, if you want something that has a band gap of 1.8 electron volts, you could take gallium arsenide and aluminum arsenide, alloy them together, and in just the right proportion, you would get something on this curve right here that has a band gap of 1.8. And the band gap, again, affects the absorption and also the emission of the material. You can also affect the band gap by the structure of the material. So quantum dots are something, for example, that is really small particles of semiconductors. And if you make them small enough, what's called quantum confinement starts being important. That is, again, as you may have learned in physics 222 or equivalent, when you make your box narrower and narrower, the energy levels kind of get squeezed upward. And so you can control emission wavelengths by controlling both the composition and also the structure or size of the material. Okay, going back to the band gap and the empty states up here and the filled states down here. If you have a free electron, the energy is related to its momentum through this formula from physics 121. De Broglie says momentum is related to a wavelength, and we have already said wavelength and wave number are inversely proportional. So if I've done things correctly, which maybe I'm missing a divide sign here. Anyway, you end up with this this formula for the energy levels, or the relationship between energy and momentum for an electron. This is called the dispersion. And so this is predicting a parabola. And what we basically get here in the conduction band is exactly that, a parabola, at least if you sort of squint your eye and don't look too closely. The parabola that you get, however, inside your material is different than the parabola that's predicted for a free electron. And so the way we describe that is using a concept called effective mass. The effective mass describes the curvature of the parabola. And if you have a small amount of curvature, you end up with a large effective mass, which means that you change the momentum by a lot, but the energy only changes by a little bit. Conversely, if you have a big curvature here, you can have a small effective mass, and then the reverse happens. So that's one way we talk about electrons in solids, is through the effective mass. But if you look at these bands down here, these are parabolas, but flipped the opposite way. And that means they have negative effective mass, if we want to use the same parabola model. And because we don't like things that have negative mass, we pretend like there are particles that act like sort of anti-electrons, which we call holes. So the hole is the absence of an electron, and the hole has a positive mass, whereas the electron itself in these bands would have negative mass. The hole is an example of what's called a quasi-particle. Quasi-particle is basically something that acts a lot like a particle, but maybe isn't exactly. And for that matter, electrons here, when we start talking about effective masses, are also quasi-particles, because real electrons don't have strange masses. They just have the normal electron mass. So both electrons inside these bands and holes inside these bands are examples of quasi-particles. There's another quasi-particle that I'll be talking about next, which is called the exciton. This is a bound state between an electron and a hole. A hole acts like a positive particle, electron negative particle, and so they're attracted to each other, and they can form bound states that are a lot like hydrogen atoms. And they can be described by the binding energy, which is how much energy it takes to split them apart. And because it takes energy to split them, when the exciton forms, it actually has a lower formation energy than just having the electron and hole separate from each other. Okay, that's your introduction to semiconductors. Now to talk for a couple minutes about solar cells, which use semiconductors. How a solar cell works, generally speaking, is this type of device structure. You have two types of semiconductor, one that has some added impurities to give it some extra electrons in the conduction band, one that has some added impurities to give it extra holes in the valence band. When a photon is absorbed, it excites an electron from the valence band to the conduction band. That produces an electron in the conduction band and also a hole in the valence band. The electrons get funneled off towards the top. The holes get funneled off towards the bottom. Meanwhile, in the wire here, this is just a regular metal wire in which electrons flow. So the electrons kind of go out here, go around your circuit, and then come back over here where they meet up with the holes that have been funneled down towards the bottom. And that's the electrical circuit in a solar cell. And you can use that current that's produced to power a load, like lighting the lights in your house or something like that. So solar cells take this absorbed optical energy and produce electrical energy. And absorption, as I mentioned, is governed by the band gap. So it'd be a natural question to ask, what band gap do you want for your solar cell absorber? Here is the same band gap engineering plot from before. Here is the solar spectrum that reaches the Earth's surface. And so then the question is, well, should we use gallium arsenide, which has a band gap about here? Silicon has a band gap here. Maybe, I don't know, cadmium sulfide, which has a band gap about here. Like, what do we want for our band gap? Well, there's two things to keep in mind. One is if your band gap is small, then it can absorb not only at the band gap, but everything, all the photons that have higher energy than the band gap. So that sounds like a good idea. You want to absorb lots of photons from the sun. If the band gap is large, you're not going to absorb the photons because they won't be able to kick up the electron into an available state. But also, you don't want too small of a band gap, because if you have too small of a band gap, then photons with higher energy than the band gap will get kicked up into a high energy level, and they will lose their energy primarily through phonons, which cause heat. And I'm not going to talk about phonons in this talk, but just keep in mind they lose energy. So this was analyzed in 1961 by Shockley and I don't know if this is Queisser or Queisser. Most people say Queisser. And they determined that the best possible band gap is 1.34 electron volts. And this would give rise to an efficiency of 33.7%, meaning that's the fraction of energy that's turned from photons into electrons in your solar cell circuit. And at that energy, all of these photons over here get absorbed. You don't want a higher band gap energy because, as I mentioned, then a lot of your photons won't be absorbed. And you don't want a lower energy because your electrons will be kicked too high into the band and you'll lose energy due to heat. So this is kind of the sweet spot right here. And it turns out silicon is not too far away from that sweet spot. So the maximum possible efficiency, about 34%. Silicon has an efficiency of about 29%. And silicon is very common and well-known and easy to process. And so that's why pretty much all of your commercial solar cells these days are made out of silicon. But there are lots of other possible materials. And so one of the things that NREL does is keep track of efficiencies for different materials, and they produce a plot like this, which you can find on their website. Just Google solar cell efficiencies NREL, and it will pop right up. And so this is when the material was produced and what the efficiency was, and different colors indicate different types of materials. The blue colors are silicon materials. And so you can see the silicon limit that I was just mentioning is about 29%. So silicon technology has been improving and improving and improving and getting closer and closer to that theoretical maximum for silicon. The Shockley-Queisser limit of about 34% is up here. And you can see some things are getting closer to that. But there's other things that are better than that. So how do you have a semiconductor absorber that gets higher than the theoretically maximum efficiency? Well, you do it with more than one absorber. So that efficiency was calculated just for a single absorber. Here we have multiple absorbers, different types of materials to absorb different parts of the solar spectrum. Okay, so it becomes important to be able to put different materials together in order to get even more efficient solar cells. And I'll draw your attention now to these materials. These are the perovskite materials that I've been studying. And these materials have been rapidly rising in efficiency. And you can be even more impressed if you compare them with polycrystalline silicon. For simplicity, this is what most commercial solar cells are made out of. And you can see how fast the efficiency has been improving with these perovskites. So they're cool. Just this morning, literally today, I saw this news article about a perovskite silicon tandem solar cell. So you got silicon as the bottom absorber, and then some perovskite coated on top of the silicon. So very active area of research and technological development. Okay, so what are these perovskites? I've used the term hybrid organic-inorganic semiconductors. And here's basically what they look like. You have inorganic atoms partnered with organic molecules. The inorganic atoms are metal atoms, which form at the center of these octahedra, and then halogen atoms or halide atoms like iodine and bromine, chlorine, group 7 in the periodic table, that form on the corners of these octahedra. And then the corners connect to neighboring octahedra. And the organic molecules, in this case, this is methylammonium, form in the gaps in between the octahedra. But they're cool because you can use bigger molecules and split the octahedra into layers. So you get a layered structure of molecules in between, and basically a semiconductor made out of the metal and halide atoms in a sheet. And you can even, so the sheet is what's called a two-dimensional semiconductor, whereas this one over here is a three-dimensional semiconductor. But you can even do like a mixture of big and small molecules and get something in between. So this is the two-dimensional situation over here, the three-dimensional situation over here, and then here is somewhere in between where you start getting multiple layers of these two-dimensional sheets partnered together and then separated by organic molecules, and then multiple layers again. So this is what they look like, at least what one of them looks like. This is phenethylammonium lead iodide. So phenethylammonium is the molecule, lead iodide is the metal halogen sheets. And here it is mounted on one of our cryostats. And then we shine light at it to determine its properties. Here, we've actually got some green light shining on it, if you can see right there. The white light is just to make the picture possible. The sheets here cause quantum confinement, just like those nanoparticles that I was talking about earlier, where you have confinement effects that affect the energies. In fact, they bump up the band gap energies, and they also bump up the binding energies because the electrons and holes are forced into these sheets. They're closer to each other, they bind to each other more strongly. There's also important dielectric effects that happen in these materials, which probably in the interest of time, I won't get into at all. But there's a dielectric mismatch between the molecules and the metal halide things. So we want to study the properties of these excitons. It's very important. We want to measure them, we want to model them, and by measuring and modeling, then we can hopefully improve the ability to design materials to have the desired properties that you want. So typically, to measure the band gap, what you might do, this is back in the 1960s, you might measure the optical absorption. And as I mentioned before, the absorption starts when the photon has at least as much energy as the band gap. If you have photons with more energy, they're also absorbed. And so you get some sort of plot like this, where this is absorption increasing and increasing, but the place where the absorption starts, that's the band gap. So that allows you to identify the band gap. You can also, in many materials, look at the emission and look at where the emission happens, and that will also mark the band gap in many materials. But in materials where excitons have big effects, which is the case for these perovskites, it actually, as I mentioned, takes less energy to create an exciton than it does to create separate electron holes. And so you get like excitonic related peaks here that mask where the band gap is. And you can't even really tell in this material just by looking at the absorption where the band gap is. And that's the case with our perovskite materials as well. So we measure the absorption. This is, these are excitonic related peaks. And then somewhere in here is the band gap, but where? And there's been a lot of disagreement with published reports in the literature for lots of different types of perovskites about what the band gap is. And the binding energy is the difference between the excitonic absorption and the band gap. That's a really important quantity to know. For example, in a solar cell, you're producing an electron hole pair. The electrons are going one way, the holes are going the other way. So you have to separate the electron and hole, which means you have to overcome the binding energy. And so you better know what that binding energy is when you're designing your solar cell. But it's really hard to tell. So a lot of what we've been doing is to try to solve this problem. And our solution is to apply an electric field and use the Franz-Keldysh effect to figure out what the band gap is. To apply an electric field, we produce our materials on top of interdigitated electrodes. So you got metal wires really closely spaced, interleaved with each other. And then we apply voltages to these electrodes, which sets up electric fields between the electrodes. And the Franz-Keldysh effect says when you apply an electric field to your semiconductor, you get a transfer of the absorption strength from above the band gap, so this absorption up here, to below the band gap. So you get absorption down here where previously you wouldn't have had absorption. And this is indeed what we see. So this is now butyl ammonium lead iodide. Here's the absorption for butyl ammonium lead iodide, and we were able to identify this right here as being the band gap by looking at the electric field response. And when we turn on electric fields, we get an increase in the absorption here, a decrease in the absorption here. So if you look at the difference, basically right in the middle there is where the band gap is. And this is called electroabsorption, just the difference between the absorption with the electric field on compared to the electric field turned off. And here's what our electroabsorption setup looks like. We start with a white light source, pass it through a spectrometer to select out what color we want, focus it into our sample, which is mounted in this cryostat here, so we can look at the temperature dependence and see things at very low temperatures. And then we've got a detector over here, and we use a technique called lock-in detection that I won't get into. And being able to make these measurements allows us to do things like see what happens when you substitute different halide atoms. So change it from iodide to bromide to chloride, for example. If you look at right here, this is that Franz-Keldysh feature. We can measure the band gap here and here and here. And we can then measure the binding energy as being the difference between this excitonic absorption and where the band gap is. And this basically had not been done before, at least not with any degree of precision. We were also able to look at bromine, chlorine alloys and some other alloys also, and see here is a plot of the ratio, and then the binding energy increases with the amount of chlorine, and then the band gap also increases with the amount of chlorine. So we can tell that in between complete bromine and complete chlorine, we are getting some good alloying such that the properties are kind of the average of the two extremes. We can also look at temperature dependence, and we see a change in the electroabsorption line shape going from low temperature to room temperature. This is related to disorder through the Stark effect, but unfortunately don't have any time to talk about that. But what we did was measure just a whole bunch of materials, just anything that we could make, and then measured the band gap energy and the exciton binding energy for all of these materials. And you can see a clear correlation between the two. And this was something that was thought to exist, but nobody had really seen before. So this is new. But we were able to go even farther than that. With these precise measurements, we were able to do a precise model. And there are basically two competing models in the literature for these materials. One is you just say the electrons are confined to a two-dimensional plane. You got these organic molecules out here, but nothing's really happening. The electrons and the holes, so the excitons just stay here in the plane. And that's actually the model that pretty much everybody was using. But there was a more complicated model saying, well, electrons are mainly here, but electrons are waves because of quantum mechanics, and the wave functions could penetrate in through this barrier into this neighboring well. And so maybe you get some communication between layers. And if this model is correct, you would not find any dependence on the barrier length. But if this model is correct, as the barrier gets smaller and smaller, you get more and more communication, which will decrease the binding energy of the excitons. And so one of the things we did was to produce a series of perovskite materials that had different length of organic molecules, ranging from pretty short to pretty long. And then we did our absorption measurement, our electroabsorption measurement, and this is the result of the binding energy versus the barrier length. So there is a clear dependence between the two. And again, this was something that no one basically had not been seen before. There was one really old report that nobody followed up on. And so this is very good evidence that the superlattice model, so communication between layers, is what we needed to do. I will skip over the math here and just mention that in order to make calculations within this model, which was developed in the 80s and 90s, there are basically 5 parameters that you need. You need something called the exciton effective mass, which relates to the effective mass of the electron and the effective mass of the hole. You need the length of the barrier, the length of the well, and also these dielectric constants. We could get the effective mass from density functional theory, which we have some collaborators that do that type of theory, and we could measure X-ray diffraction and get the structure of the material, which gives us the width of the well and the barrier. But we run up against some issues trying to figure out the dielectric constants to use in this model. Because when you measure a dielectric constant, or even when you calculate a dielectric constant, you're getting the dielectric constant of the whole material. And this model requires separate dielectric constants for the wells and the barriers. but doing something really clever, this is Cameron's idea, to do a weighted average of the barrier and well dielectric constants, and say this is what the dielectric constant of the overall material is. And then we could figure out, by doing a bunch of measurements, we could do some fitting and figure out what the barrier and the wells would need to be. And it turned out to be pretty self-consistent, and gave us the values we needed for the theory. There was another headache, which is that the dielectric constant depends on frequency. And so there's the question of what frequency dielectric constant should we use? And that is its own story that I won't have time for today. But there are three key results that I want to present from this work that prove that we actually know what we're doing. So this is the same numbers that I plotted before, the dependence of barrier length of the binding energy, where you can see for short barriers, you get a really small binding energy. Well, using this theoretical framework from the 80s and 90s, we could deduce what the well and barrier dielectric constants needed to be, and then use those in the theory with the effective mass from the from some other theory, and almost get an exact match. This one here was problematic, but the experiments are the open circles, the theory are the asterisks. And we fit this data to give us these dielectric constant values, but then using these values, we looked at a different structure of these perovskites, a different phase, and with no additional fitted parameters, we were able to exactly predict what these binding energies should be. So we think that we do know what we're doing. Here's that plot from before of all of the materials we measured. By varying parameters systematically in this theory, we could tell that the three most important parameters are actually the excitonic effective mass, the well dielectric constant, and the barrier length. And we could predict what kind of changes those are all going to make. And so if we want to get a particular band gap energy and a particular binding energy, we know how to tailor the material to do that. I think I'll skip through that because time is getting short. But this gives us not only the capability to do band gap engineering, but also exciton engineering. Because these perovskite materials are very easy to produce, you basically mix chemicals together and then spin the thing, and the chemicals will react and deposit on a surface. You can easily, well, potentially anyway, easily make multi-junction solar cells. And these 2D perovskites can aid 3D perovskites. The 3D ones tend to be a little bit better for solar cells than the 2D type that I've been talking about here. But you can partner them together to kind of get the best of both worlds. So there's a bunch of ongoing research that we have here. We've got partners from the University of Kentucky that are making tin-based perovskites, changing different organic molecules to impact the polarization. We've got University of Utah collaborators that are studying the effects of water on this particular molecule. Water turns out to be a real source of degradation if you want to make these perovskite materials like to go on the roof of your house. We're not quite there yet. We've also got some partners at Duke University that are making what we call 1.5 dimensional perovskite ribbons. So these ribbons extend into and out of the plane of the board there, and you can control the width of the ribbons. If you just have a single octahedron that extends into the board, that's like a wire. That would be a one-dimensional material. If you've got a plane of octahedra, it's a two-dimensional material, but here it's somewhere between a wire and a plane. And then lastly, NREL and some other places as well are making what's called chiral perovskites. In this case, the organic molecules that you use have some helicity to them, which means that you have two different versions of the same molecule, one that's left-handed and one that's right-handed, kind of like DNA can spiral that way, or could spiral that way. And those can impact the metal halide layers, and it's thought they give almost like a twist to these inorganic layers, producing chiral properties for the electrons. And chiral is interesting because chirality can be related to things like circularly polarized light. So you could get a detector that detects circularly polarized light that's right-handed better than it detects left-handed circularly polarized light, or sources of photons that produce circularly polarized photons of one helicity or the other. So some cool things there. Okay, it looks like I'm down to maybe 5 minutes or so. So I need to talk a little bit about NREL. It is one of the DOE national labs. It's there in Colorado. And it's the only national lab whose specific mission is to look at renewable energy. The National Renewable Energy Lab. And they've identified 3 primary goals here: combating climate change, pollution, and loss of biodiversity, which is also related to climate change. And they do a lot of different types of research, but one of the main ones is solar energy research. When I was there, my desk was in this building here, my lab was over here. This building over where the lab was called the Solar Energy Research Facility. And basically this whole building is dedicated to solar energy research. It's kind of an interesting place. They try to be themselves energy self-sufficient. So you can see all these solar panels, which basically power the lab, or come close to powering the lab. I worked there with Matt Beard, who is the director of the Choice Center, which is the Center for Hybrid Organic-Inorganic Semiconductors for Energy. And he leads a team of about 16 other scientists, plus their postdocs and students that are all working on related problems with these hybrid perovskite materials. I spent most of my time there in what's called the terahertz lab, looking at the effects of terahertz radiation on these materials. And I didn't get any super great pictures of the experimental setup, so let me turn to a schematic. It looks something like this. Basically, you take an 800 nanometer pulsed laser, split it into half. You use one part of it to produce terahertz radiation. Terahertz is kind of like in between, well, it is in between infrared radiation and microwave radiation. So you can think of it as sort of like infrared beams that have some microwave characteristics. And so this one half of it produces pulses of terahertz radiation through what's called the optical rectification effect. The other part of it sends pulses into a detector, and through the Pockels effect is able to detect the terahertz radiation. So you produce terahertz, you detect terahertz, you put your sample in between, and then can see the effects of the terahertz on your sample. And there's this delay line, which allows you to have a delay between the emission and the detection. And so you can actually trace out the terahertz beam in time, like as the electric field goes up and down, which you can't do with visible light because it goes up and down so quickly. But with terahertz light, the up and down of the electric field happens on the picosecond time scale. This is some actual data I took when I was there. And you can do the Fourier transform of this to see the frequencies that you're producing. So it produces between, I don't know, maybe 0.2 terahertz and like 2.5 terahertz. And then you can see how this terahertz gets absorbed or otherwise interacts with your sample. And we're interested in this because these chiral materials, one of the thoughts is that they will have what's called chiral phonons. And chiral phonons are like rotations of the, well, It's the oscillations of the atoms in the material that form kind of a rotational pattern as they oscillate. And chiral phonons may absorb right circular terahertz more than left circular terahertz. And this mismatch between right and left absorption can cause a rotation of a linearly polarized terahertz beam. And so that's the type of thing we were looking at. Rotation of the polarization of the terahertz beam. But we have not yet been successful. One of the issues we had is we didn't have the right polarizers. As it turned out, we learned after spending maybe a month on this that our polarizers were not rated to high enough frequencies. So we ordered new polarizers. That took about another month. And then I learned another lesson, which is that lasers break. And our laser broke literally the week before the polarizers arrived. And then the laser was down for about 2 months before it could get prepared. Another lesson that I didn't write here is don't underestimate government bureaucracy. Okay, but when the laser was down, I was able to make contributions to the lab there because I was good at programming, and most of the people there were not. So I was able to do a lot of lab view and Mathematica programming to better collect the data and analyze the data. Connections are key. Through Matt and that choice group, I was able to make lots of other connections with people that are now sending us samples here to BYU. So even though a lot of the research there didn't go as planned, I'm able to continue interesting stuff here at BYU with those connections that I made. And then finally, there's this experimental law that we established in my lab here that I was able to verify there, which is called the rule of pi. The rule of pi, strangely or coincidentally, was also made public by Grace Clark in 2016, who wrote this article about her lessons learned from her career in acoustics. And this is how she framed the rule of pi, which is, in order to estimate the actual amount of time required to finish a project, make a generous estimate and then multiply by pi. And that will be how long it actually takes you. My corollaries to this law is that on bad weeks, it's actually a factor of 2 pi. On really bad weeks, it can get to be pi squared. And just hope and pray it's never e to the pi, because that's no fun. And it was e to the pi for a lot of my time at NL. Anyway, I'm out of time, so let me conclude. Semiconductors are pretty cool. These hybrid perovskites are a very versatile and interesting materials system, and maybe the solar cells of the future. Excitons are really important. I feel like we've made some key contributions there. It's important to find good collaborators. We rely on chemists basically to make these materials for us. Things don't always go as planned, but you can always make contributions. And when you make them where you can, you will add to your list of collaborators. So thanks for your attention.
Time for just 1 or 2 short questions.
Yeah.
Maybe just a comment. David already has an explanation for the rule of 5, such as going around in circles.
Very good. Other questions? Yeah.
Yeah, I was gonna ask about the efficiency, like, so the efficiency is like 30 or 50% or something, not like in that big long chart you showed us. How does that compare to other things? Like, is wind at like 99% or is wind at like 1%?
Oh, yeah, that's a good question. I don't know. I haven't researched wind too much.
Okay, or like, you know, petrol or whatever.
Yeah.
But, okay. Just curious.
Well, I mean, the nice thing about solar cells is that, like wind, they're a renewable energy source, right? We don't use hydrocarbons, and you don't put carbon into the atmosphere. And the sun produces a lot of energy, and not much of that reaches the earth, but like compared to other energy, like it's still a lot that reaches the earth. So I do think solar energy is going to be more and more important as we go into the future.
So again, on efficiency, why perovskites? Because looking at that efficiency graph, there are like the multi-layered solar cells that are up in 40, in the 40s, and right now the perovskites are just around 25.
Well, that's single layer perovskites. There are multi-layer perovskites that are getting more and more efficient as well. Yeah, I didn't talk about those too much. But yeah, so perovskites are basically very good at absorbing light. The experiments that we've been doing, we typically just have like a couple of 100 nanometer thick layer of these perovskites. So really, really thin coating, and yet, you know, it's still visible. Like you can see it's interacting strongly with light. So that's one of the best things about perovskites is just how strong the interaction with light is. Yep.
You mentioned that you guys typically get these made for you. Like, how do you go about making these eco?
Yeah, so it's a lot like magic. So basically what you do is you put in a solution that contains the metal atoms, that's the yellow ones in this, and also a solution that contains the iodine atoms, so that's the green ones here, and also a solution that contains these organic molecules, and you put them in the right proportions, and these are in solvents, and then so you stick them on your surface, like kind of squeeze them out onto the surface, and then you spin it, which causes these solvents to evaporate quickly, and then they just assemble into these things on their own. That's the magical part. So this is called self-assembly. And yeah, you just get the right mixture of this called precursors, and they just do this for you. Now you need to do this in a very pure environment, and with very pure chemicals. And I'm sure there's other things that I don't know because I'm not a chemist. But fortunately, I know lots of nice chemists. And yeah, so we're good at doing these optical experiments, and the chemists are good at producing the materials.
Thank you, speaker. One more time.